Alright, welcome back everybody, and today's a bit of a special video. We're going to be going over the 2020 Methods Exam 1 solutions. So this exam happened today actually. I just sat the exam a couple hours ago at 9 o'clock. Now it's like 3 o'clock, so just 6 hours ago. And yeah, it was quite an interesting exam. A couple of spicy questions in there, a lot of algebra and arithmetic and all that, but overall it was a pretty good exam. So we're going to be going over the questions one by one. I'm going to show you my thought process during the exam, what I thought about, what I did and whatnot. And yeah, let's just get straight into it. So for the first question, question 1a, we're given y equals x with sine of x. We have to differentiate that thing. That's not too bad to do. That's this product rule. So if you call this thing v and this thing u, well, the product rule says it's equal to vu dash plus uv dash. So here you have sine of x times u dash, but u dash is 2x, so we'll multiply that out the front, and then plus u, which is x squared, times v dash, I've got a dash there, v dash, which is this cosine of x, because derivative of sine is cosine. So that's your answer to question 1a. For question 1b, you're given this other function, e to the x squared minus x plus 3, and you're asked to, well, first differentiate it and then evaluate the derivative at 1. So let's differentiate this thing. If you differentiate e to the something, well, it's just e to the something itself, and then you have to multiply by the derivative of the inside, which is just 2x, so power rule right here, and then minus 1, like so. So this is f prime of x, and now we just have to evaluate f prime of 1, so you just plug 1 into all the x's, we're going to get e. Now x, well, 1 squared minus 1 plus 3, well, 1 minus 1 is 0, so you're left with e to the 3. And then if you plug 1 into here, well, 2 times 1 minus 1, that's just 1, so this becomes your answer. So for the next question, question 2, we're given a little bit of probability. This surprised me a little bit during reading time because usually you don't see probability on the second question of the exam. But yeah, we have this right here. And I've got to mention as well, I'll be putting some photos of the exam for your reference in the description below. This isn't what you would see on the exam. This is information that you would extract out of the question when you're doing the exam, but yeah, let's just try and work our way through this. So question 2 is asking us to find the probability that some car requires an air filter and no oil filter. So air and intersect, no oil, so oil prime, I guess. So we're given that the probability of requiring an oil change is 17/20. The probability of an air change, or whatever it's called, is 3/20. And the probability of both is 1/20. So the first thing you want to do is draw up a little Venn diagram. So you know the probability of all of this oil, the probability of getting an oil change is this whole circle, which is 17/20. Same thing for the air, it's this whole circle, which is 3/20. But the probability of having both is in the intersection, and that's 1/20. So in order to figure out each of these parts of the circle independently, you simply take, for example, the oil probability and you just subtract 1/20. So this over here becomes 16/20, and over here, well, air is 3/20 and you subtract 1/20, so that just becomes 2/20, like so. So as you can see, that once we have the Venn diagram, it becomes pretty easy to figure out what this probability is. We want to figure out the probability of having an air change without an oil change, so that's just this section right here, which is 2/20. So the answer to question 2a is just 1/10. And for the next question, we get something a little bit similar, but we get some parameters or variables instead of actual numbers. So if the probability of an oil change is now m over m plus n, where m and n are just some random real numbers, probability of an air change, we're given that's n divided by m plus n, and the probability of having both changed is 1/m plus n. And we can use the same method as before. We know the probability of both is in right here, so that's 1/m plus n. And notice all these have the same denominator, so we can work with some addition and subtraction quite easily. So the air change is this whole entire circle, and that's n over m plus n. But since we only want to figure out this section, we subtract off the intersection. So that's going to be n minus 1 over m plus n. And then same thing for the oil, we get m, and we subtract off this intersection, so m minus 1 over m plus n. And we have to find m in terms of n if the probability of having an air filter change without an oil change, so oil prime, like so. We have to find m in terms of m if this probability is equal to 0.05. So how do we do this? Well, we want air intersect no oil, so that's this section of the Venn diagram. So this probability we know is n minus 1 over m plus n, and that's equal to 0.05, which is 1 over 20. And doing a little bit of rearranging and whatnot, we get that 20 times n minus 1 is equal to m plus n. And we can keep going, expanding this out, we get 20n minus 20 is equal to m plus n, and the question asks us to find m in terms of n, so we just subtract off n from both sides, and we get that m is equal to 19n minus 20, and that's the solution. For question 3, we're given this tan graph with some unknown parameters. So we have two unknowns, but we're also given 2 points on this graph, and we're asked to find a and b. So the first thing that should jump to you is that you should find some kind of system of equations, so 2 equations to work with. So the way you do that, that's quite easy. You just sub in each of these points into this equation. So let's take a look at this first point. We get that if you plug y equals -1 and x equals to -1, you get that -1 is equal to tan of minus x. Sorry, not minus x, we should plug -1 into the x, so minus a plus b. And if you take a look at this point, well, y is square root of 3. And if you plug 1 in for x, we get tan of a plus b, like so. And well, let's take inverse tangent on both sides, because ideally we kind of want to isolate a and b. So if you take inverse tangent on both sides, you find that inverse tangent of -1 is equal to minus a plus b. And you get that inverse tangent of root 3 is equal to a plus b. And what's inverse tangent of -1? Well, it's minus pi on 4. And that's equal to minus a plus b. And you might say, well, there's also other angles such that the tan of those angles give you -1. But if you look on this picture right here, notice that it's the first time that this tan graph hits -1 after it passes 0. So it has to be minus pi on 4, which is the first solution. And then also tan inverse of root 3, well, that's pi on 3. So that's equal to a plus b. And now you have something that's pretty easy to solve. Let's add these 2 equations together, and you should get pi on 3 minus pi on 4, which is pi on 12. And that's equal to, well, minus a plus a, that's 0, and b plus b, that's 2b. So you find that b is equal to pi over 24. And now let's plug b back into one of these equations. Let's choose, I don't know, this equation, for example. So for this equation, the second equation, if we want to find a, then we'll just have to subtract b on both sides. So that's pi on 3 minus pi on 24. And a is now equal to, well, if you multiply top and bottom here by 8, you get 8 over 24. 8 minus 1, that's 7 pi over 24. So a is 7 pi over 24, and b is pi over 24. So for the next question, we're given this log equation, and we're asked to solve for x. So the first thing that I kind of thought of doing was, what we want to combine these 2 logs together using some log properties, but we have this 2 that's kind of in the way. So let's bring that up to the exponent. So now we have log base 2 of x plus 5, but the whole thing squared, minus log base 2 of x plus 9 being equal to 1. And now, since we just have, well, just some log base 2 and another log base 2, we can combine these. Since there's a negative, we divide this inside by this inside. So we now have log base 2 of x plus 5, but the whole thing squared, divided by x plus 9, and that's equal to 1. Okay, and now we can raise both sides to 2. So if you raise the left-hand side to 2 and raise the right-hand side to 2, this 2 and this power of log base 2 kind of cancel each other out, and you're left with what's inside right here. So that's x plus 5 all squared, divided by x plus 9, and that's going to give you 2 to the 1, which is 2. And now you can bring this x plus 9 onto the other side, and you get some kind of quadratic. So now we have x plus 5 squared being equal to 2x plus 18, so multiplying this x plus 9 by 2. And now we just have to expand things out a little bit, so now we get x squared plus 10x plus 25 being equal to 2x plus 18. And now let's try to simplify that a little bit. Let's go over here. So subtracting 2x on both sides, we get x squared plus 8x, and subtracting 18 from both sides, we just get a plus 7 right here. And that's equal to 0 because there's nothing left on the right hand side. Now let's try to factor this out a little bit. So this is x plus 1, x plus 7, because notice 1 times 7 is 7, and 1 plus 7 gives you 8, and that's equal to 0. And now this is pretty easy to solve. We just simply do the null factor law. So take the case where x plus 1 is equal to 0, well, x is equal to minus 1, and take the case where x plus 7 is equal to 0, so x is equal to minus 7. Now you just have to make sure that both of these, you just have to make sure that these solutions work in terms of the original equation. So if you take a look right here, if you plug in minus 7 into the second log, you get minus 7 plus 9, and that's equal to 2. So log base 2 of 2 works because 2 is positive. But if you take a look on the first log, if you plug in minus 7, you get minus 7 plus 5, but that's equal to minus 2. So you get some kind of imaginary number that's not real, and hence for the real case, we're doing methods, not specialists. So for the real case, you can't have x equals to minus 7 because it will be undefined for this first log. So you're left with x being equal to minus 1. If you plug minus 1 into here, you get 5 minus 1, which is 4, which is positive, so that's good. And same deal over here. The inside will be positive, x equals minus 1. So the answer is x equals minus 1. So question 5 gives us a little bit more probability. This is a binomial question, and it says that for some certain population, the probability of a person having this gene, which they called like SPGEI or something in this question, is 3/5. So here we have some kinds of binomial distribution, and the probability of someone having this gene is 3/5. And part A asks us to find the probability that for 4 people, so number of trials is 4, it asks us what's the probability that 3 or more people have this gene. And in fact, this is the question where I lost the mark, I think, because I didn't even know what I was doing in the exam. I somehow ended up calculating the probability that x is less than 3. Maybe I didn't even know. I understood the question. I probably wrote the inequality sign wrong and then just did the wrong calculation from there. I didn't even know, but it was a pretty stupid way to lose a mark. Yeah, but oh well, let's just go on with the solution. So probability that x is greater than or equal to 3, well, that's the probability that x is equal to 3 plus the probability that x is equal to 4, because you only have at most 4 people in this little sample. So let's see, how do we find this probability first? We can use the binomial formula, which is n choose x. So n in this case is 4, so 4 choose 3, times the probability of success raised to the third power times the complement probability, which is 2/5, raised to n minus this number, which is 4 minus 3, which is 1. And then for the second probability, well, we have x equals to 4, so we do 4 choose 4, so n choose 4, times probability of success, so 3/5 raised to the 4th power, and then 2/5 raised to n minus this x value, which is 0. So 4 choose 4, that's exactly 1, because there's only one way to choose 4 things from 4 things, and 2/5 raised to the 0 is 1 as well. And 4 choose 3, if you have 4 things and you're trying to find the number way, so you choose 3 things, well, there's 4 ways to do it. And you can confirm that for yourself by using the NCR formula, so that's 4 factorial over 3 factorial times 4 minus 3 factorial. 4 factorial is 24, 3 factorial is 6, 4 minus 3 is 1, 1 factorial is 1, so 24 divided by 6 is indeed 4. And now we just have to do a little bit more arithmetic, so 4, and now we have 3 cubed, which is exactly 27, and 5 cubed is 125 times 2/5, not 3, 5. And then plus, now 3 to the 4 is exactly 81. And then 5 to the 4, well, we know 5 cubed is 125, so multiply that by 5, you get 625. And, well, let's see, 4 times 27, that is, let's see, that should be 108, if I'm not mistaken. Let's actually do this. So that's 28, 2 times 4, yes, it's 108. So 108 over, now we know 125 times 5 is 625. And then we have plus, actually, we have to multiply by 2 as well. So this in fact becomes 216. And then plus 81 over 625. And if you add these two together, you should get 297 over 625, like so. So that's the answer. So for part B of this question, we're using the exact same distribution, but we have to find this conditional probability. So the probability that there's exactly 2 people with this gene, given that at least one person has it. And there's actually an extra bit of info to this question. We have to answer in this specific form. So a cubed over b to the 4 minus c to the 4, where a, b, and c are positive integers. So the first step is to, well, use the conditional probability formula for this. So that's the probability that x is equal to 2 and it's greater than 1. And the only way for that to happen is x is equal to 2. And this is divided by the probability that x is greater than or equal to 1. Next, we can go through and use the binomial formula for each of these probabilities. So for x equals 2, we have 4 choose 2 times the probability of success raised to the second power times the complement probability raised to 4 minus 2, which is 2. And then divide this by. Now for the probability of x is greater than or equal to 1, it's a little bit more tricky, but notice that if you consider the probability that no one has it, then if you take 1 minus the probability that no one has it, then that's the same thing as the probability that at least one person has it. So we have this form right now, and we can use the binomial formula again for the probability that x equals 0, so that's 4 choose 2. Actually, we can do a bit more work at the top. So 4 choose 2, if you use the NCR formula, you get 6. And we have 3 squared, which is 9, times 2 squared, which is 4, divided by, now we have 5 squared times 5 squared, but I'm actually going to write that as 5 to the 4. That's going to be useful later on. Then we're going to divide this by 1 minus probability that x equals 0 is 4 choose 0, so n choose 0, times probability of success, so 5/3 or 3/5, times or to the 0th power, and then complement probability raised to n minus 0, which is 4. And now let's keep going. We have 6 times 9 times 4, but 6 times 9 times 4, that's 36 times 6, but 36 is 6 squared, and if you're multiplying 6 squared by 6, that's 6 cubed, so 6 cubed divided by 5 to the 4, over 1 minus, now 4 choose 0, well if you have 4 things and you're trying to choose 0, there's only one way to do that, and 3/5 to the 0 is again equal to 1, so you just have the 2 to the 4 over 5 to the 4, And as soon as I got this, I immediately knew what to do, because we have a 5 to the 4 on the denominator right here. So I guess the most logical way to get this answer into this form is to multiply the top and the bottom by 5 to the 4. So 5 to the 4 like so. And if you do that, this and that will cancel, leaving us with 6 cubed over. Now multiplying 5 to the 4 into this one, we get 5 to the 4 minus, and this 5 to the 4 will cancel with this 5 to the 4 on the denominator, leaving us with 2 to the 4, and that's the answer. For the next question, question 6, we're given this function f of x being equal to square root of x divided by square root of 2, defined on the interval 0 to 2. And part A asks us to find the inverse function, and we have to find the domain of f inverse as well. So in order to find the inverse, that's not too hard to do, just switch x and y around. So now we have to solve x being equal to 1 over the square root of 2 times the square root of y. And to solve for y, let's see, we can multiply both sides by square root of 2 first of all. So square root of 2x is equal to square root of y. And now to isolate y, we just square both sides. So y is equal to root 2 squared is 2, and x squared is x squared. So y is equal to 2x squared. That means f prime of x, f inverse of x, is equal to 2x squared. And as for the domain, well, if you look at the original graph, this graph is actually given on the exam. Notice that the range of f of x is from 0 to 1. That means the domain of the inverse is from 0 to 1 as well. So what I wrote on my answer booklet was, well, we have the map f inverse going from 0, 1 into the codomain R, and then I wrote, f inverse is equal to 2x squared, and I also stated that the domain was x element of 0, 1, and that was my answer. And for part B, we have to sketch this inverse function. So we know f of x, or f inverse of x, is equal to 2x squared, and we have to sketch this on the graph right here. And that's pretty easy to do. Notice that when you sketch the inverse, the endpoints are the coordinates are kind of reversed. So the endpoint right here would be 1, 2 instead of 2, 1, and the endpoint would remain the same for this bottom one as well. And you have the curve that looks something like this. So this thing is f inverse of x. And we also have to label the points of intersection, so we have to figure out where 2x squared is equal to 1 over root 2 times root x. Notice that the intersection over here lies on the line y equals 2x. So what we can do instead is solve for where 2x squared is equal to x, and that gives us the solution that x equals 0, which is over here at the origin. Or if you cancel some x's out, you get 2x is equal to 1, which means x is equal to a half. So this coordinate, this intersection point, is in fact 1/2, and since it lies on the line y equals x, the y coordinate is also equal to a half. For part C, we have to find the area, which is defined by the area bounded by f and f inverse, plus the area bounded by f inverse and line x equals 1. And the way to do this is to kind of draw this on your graph. You'll have a much more easier time if you actually sketch things out a little bit. So first of all, the area bounded by f and f inverse, that is simply going to be this area in here. So we're going to label this area region 1. And for the second area, we have, this isn't probably the best to scale graph, but we have the line x equals 1 that's running all the way down over here. So this is x equals 1, and the area bounded by f inverse and x equals 1 will be this tiny little slither in here. So we'll call this over here region 2. And we have to find the sum of these two areas. And well, the way to do that is just to use some integration, and we're going to find the area of each of region 1 and region 2 separately and then add them together at the very end. So to find region 1, what I did was instead of calculating the integral of the top function minus the bottom function, what I did, I don't really want to integrate square root of x because you'll make more chances of mistakes doing it that way, in my opinion. So what I did, instead of calculating this whole area, I divided it into 2, because notice that these two functions are symmetric across the line y equals x, and I found this bottom area instead. And that turns out to be the integral from 0 to 1/2 of x minus the bottom function, which is 2x squared. And notice the functions right here are really quite nice. So this integral gives you the area of this bottom region, but we also have to multiply it by 2 to get the full area. So 2 times this integral. And to evaluate this, that's not too bad. So that's 2 times antiderivative of x is 1/2 x squared. Antiderivative of 2x squared is 2/3 x cubed. Evaluate this from 0 to 1/2. Notice if you plug 0 into all of this, you're going to get 0, so we don't even have to worry about what happens at 0. We just have to plug 1/2 in, so that's 2 times, now we have 1/2 times 1/2 squared minus 2/3 times 1/2 cubed. And I did a nice little trick. I factored out 1/2 cubed. If you don't see it right here, 1/2 times 1/2 squared. Well, you just add 1 to the exponent, which becomes 1/2 cubed. I factored out 1/2 cubed, and you get 1, and you get 2. So these are all equal. Forgot to put an equal sign. This is 2, 1/2 cubed, and then what you're left with on the inside is 1 minus 2/3. And well, 1/2 cubed is 1/8. 1/8 times 2 is 1/4. So you're left with 1/4 times 1 minus 2/3 is 1/3. That's going to give you 1/12. So the area of region 1 is equal to 1/12, like so. And now to find the area of region 2, well, region 2 is equal to the integral from 1/2 to 1. So since we're finding this area, it's bounded by the line x equals 1/2 and x equals 1. So we're going from 1/2 to 1 of top function minus bottom function. But the top function is 2x squared, and the bottom function is 1 over root 2 times root x dx. And now let's evaluate this integral. We have antiderivative of this thing, that's a 2x cubed over 3. I'll just write it as 2/3 x cubed actually. So 2/3 x cubed minus, and now we have 1 over the square root of 2. And notice square root of x, that's just x raised to the 1/2. So in order to anti-diff that, we're going to add a 1 to the exponent, so that becomes 3/2, and divide by 3/2, which is the same as multiplying by 2/3, and evaluate this from 1/2 to 1. And now let's see, what do we get? If we plug 1 into everything, we get 2/3 x. If you plug 1, if you have 1 right here, 1 cubed is 1, and then minus. Now we can do some simplifications right here, because 2 divided by square root of 2 is just the square root of 2 itself, so we can ignore that. And if you plug 1 into here, well, 1 raised to anything is just 1, so we're left with root 2 over 3. So that's the first part of integration, and then we subtract off this antiderivative evaluated at 1/2, so that's 2/3. 1/2 cubed is 1/8 minus root 2 over 3. And now over here, x to the 3/2. If you have 1 in here, you're going to have 1/2 to the 3/2, but that's exactly equal to 1 over 2 to the 3/2. So 1 over 2 to the 3/2. But notice that this is the same thing as 1 over square root of 2 cubed. But notice square root of 2 cubed, you can write that as root 2 times root 2 times root 2. So 1 over root 2 times root 2 times root 2. And these root 2's cancel each other out. leaving you with just 1 over 2 over here. So in the end, we get 2 minus root 2. So this is the first part of integration, divided by 3, minus, and now over here, we can do some simplifications. This is 1/12. Because 8 divided by 2 is 4, so, and then 3 times 4 would give you 12. And then over here, you get 1 divided by 3, and this is 2. So 3 times 2 is 1/6, so minus 1/6, like so. 1/12 minus 1/6 is exactly minus the 12th, but you have a minus right here. So this becomes 2 minus root 2 over 3 plus 1/12, like so. Okay, so we found the area for region 2. Let's worry about all of this working out. And to find the total area, we just simply add those two together. So in the end, region 1 plus region 2 is equal to 1/12 plus 2 minus root 2 over 3 plus 1/12. But we want to combine everything together nicely, so let's multiply this fraction by 4 over 4. So if we do that, we're going to get, well, this becomes 2/12 plus 8 minus 4 root 2 divided by 12. So multiply both top and bottom by 4. And this becomes 10 minus 4 root 2 over 12. And dividing top and bottom by 2, you end up with 5 minus 2 root 2 divided by 6, and that is the answer. For question 7, we're given this function f of x being equal to x squared plus 3x plus 5, and part A simply asks us to show that the point P 1, 0, which lies right over here, so x equals 1 and y equals 0, doesn't lie on this function. This is such a stupid question, I don't even know why they asked it, but yeah, it's really quite easy to show. You just need to show that f of 1 doesn't equal to 0, so if you plug 1 into all of these, you get, let's see, 1 plus 3 plus 5, which is 9, and obviously 9 is not equal to 0, so therefore P is definitely not on this function f of x. So that was part A. And for part B, we have to consider some points A, comma f of A, and they call this point Q. So let's say we have some point Q on here, and we have to find the slope of the line that connects Q and P together. So P is 1, 0, Q is given by whatever this is. And to find the slope of this thing, well, that's pretty easy. You just use the gradient formula. So y2 minus y1 over x2 minus x1. Let's call the second point P and the first point Q. So we have yp, xp, yq, xq. And if you plug all these values in, well, yp is exactly equal to 0. yq, well, yq is f of a, but f of a is just f of x evaluated at a, which is minus a, which is a squared plus 3a plus 5. And then we divide this by xp, which is 1, and then y, and then xq, which is a, so 1 minus a. And notice if we multiply the top and the bottom by minus 1, probably should have done this the other way around, but if you multiply the top and bottom by minus 1, the denominator switches over and you get rid of this negative. And yeah, that's your answer pretty much. And for part B, we're asked to find the slope of the tangent at the point Q. So if you construct some kind of tangent over here, we have to find the slope of that thing. That's quite easy to do. You just take the derivative, so f prime of x is equal to 2x plus 3, and you want to evaluate this at the x coordinate of Q, which is a, so you just simply plug in a, so f prime of a equals 2a plus 3, and that's the answer. For part C, we're asked to find the values of a such that the tangent at x equals a passes through P. So for example, if you consider this point over here, the tangent at this point has to pass through P, and we also get another point up here somewhere. So if you draw the tangent, it also passes through P, and we have to find those a values. And in order to do that, well, you know two things specifically. You know how to find the gradient of the line that connects any points on the curve to P. And we found that from part B. It was equal to a squared plus 3a plus 5 divided by a minus 1. And you know how to find the slope of the tangent to the graph at any point. And that's equal to 2a plus 3. So if you have some point that's both a tangent to f of x and it has this gradient, and it also passes through point P, so the line also has this gradient, that means these two expressions must be the same because, well, one has to be a tangent and two has to pass through point P, so these are the same. So this is a simple quadratic we can work out. So a squared plus 3a plus 5, multiplying both sides by a minus 1, that's 2a plus 3 times a minus 1, and we get a squared plus 3a plus 5 being equal to, now expanding this out, we're going to get 2a squared plus 3a minus 2a, so plus 3a minus 2a, and then we have minus 3 like so. And now subtracting 3a on both sides, those will cancel out, and let's see what else can we do. 2a squared, if we subtract a squared on both sides, we get a squared. Subtracting 5 on both sides, we're going to get minus 3 minus 5, which is minus 8. So a squared minus 2a minus 8. There's nothing left on this left hand side, so it's just equal to 0. And now we can factor out a little bit. Notice that 8 is equal to, well, minus 8 is equal to 2 times minus 4. So if you have a minus 4 and a plus 2, minus 4 times 2 is minus 8, and minus 4 plus 2 is also equal to minus 2, so this factorization works. And you get that a is equal to 4, or a is equal to 2, and that's the answer to this question. In fact, this wasn't even part C, this was part B triple I, like so. So we know a equals 4, or a equals minus 2, so a equals 4 or a equals minus 2, and part BIV asks us to find the equation of one of those tangent lines. I don't know, it's pretty stupid how they ask us to pick and choose, but whatever. So what I did in the exam was just pick 4. I just picked the positive one. So we know that the tangent, the gradient of the tangent, is given by 2a plus 3 from part BII. And if you plug a equals 4 in, you get a gradient of 4 times 2, which is 8, plus 3, which is 11. So that means you have the linear equation y equals 11x plus some kind of constant. And now if you plug a equals 4 into this f of x to find the y coordinate, you get 16 plus 12 plus 5. So 28 plus 5 is 33. So you have to sub in the points xy equals to 4 comma 33. So y equals 33. And that's equal to 11 times x, which is 4, plus a c. So 33 equals 44 plus c. So that means that c is equal to 11. So we get the equation 11x plus 11. And that's what I wrote for the exam. You can also do a equals minus 2. So if you want to do a equals minus 2, you plug minus 2 into this equation to figure out the y coordinate. So that's going to be 4 minus 6 plus 5. 4 minus 6 is minus 2. And then plus 5 is just 3. So we have the point minus 2 comma 3. And the gradient at minus 2 is, well, using this gradient formula for the tangent, we have minus 2 times 2, which is minus 4, plus 3, which is minus 1. So y is equal to minus x plus c. And subbing in this point, we get 3 is equal to minus 2, which is plus 2, plus c, which means c equals 1. So that means that y equals minus x plus 1. That should be the answer. And finally, for part C, we have to find, well, we're given some kind of transformation on this function, so f of x minus k, and we have to find the k value such that the distance between this function f and the point P is a minimum. And notice that this is just simply a horizontal translation, so you're translating this graph side to side. And the point P is actually on the x-axis. So your goal is the minimum value of this function to line up perfectly on top of the point P. So the goal is now to find the x value of this minimum, and that's quite easy to do. Take the derivative of this thing, which is 2x plus 3, set it equal to 0. So that means that x is equal to minus 3 halves. So right here, that's a minus 3 halves. And you have to translate this function over some distance such that this minimum lies above the point 1, 0. And well, you know, this distance is 3 halves. You know, this distance is 1. So 3 halves plus 1, that's 5 halves. So that means k is equal to 5 halves. Because x minus k, you're translating k units to the right. And if k equals 5 halves, you're translating this whole entire thing 5 halves units to the right, and that's going to make this a minimum line directly above this point P, which is 1, 0. Alright, so question 8 is the final question on this exam, and this is probably the most spiciest question. So the first part A, asks us to find the minimum of this function f of x, which is x times the natural log of x. So we're trying to find this coordinate q that they call it, which is the minimum. And to find it, that's not too bad. We differentiate this thing. So let's do some product rule. So v u dash is 1. So we're just left with natural log of x. And then we add this with u times the v dash. So u is x. V dash is 1 over x, so x times 1 over x is simply 1. And we have to solve where this equals 0, so we get the stationary point. So that means that natural log of x is equal to minus 1. And if you take e to both sides, e on both sides, e and natural log cancel each other out, leaving us with x being equal to e to the minus 1, or 1 over e. And now to find the y coordinate, we simply plug this back into f of x. So f of 1 over e is equal to, well, x, we get 1 over e, and then plugging 1 over e into natural log of x, well, remember 1 over e was e to the minus 1, and if you take natural log of this, natural log and e cancel each other out, leaving you with a negative 1. So you just multiply by negative 1, and that's your y coordinate. So the coordinate q is simply 1 over e, comma, minus 1 over e. And that's how you do part A. For part B of this question, we're given that the derivative of this function x squared natural log of x is equal to 2x natural log of x plus x, and we have to hence show that the integral of x natural log of x, well, it's supposed to show that an antiderivative of this function is this thing right here. So to do this, this is just some integration by recognition. So we want to somehow turn x natural log of x into this expression, and we can first do that by multiplying the integral by 2. If we multiply a 2 inside of the integral, so integral of 2x natural log of x dx, we kind of match up to what we have over here actually. So 2x natural log of x, we match that up, but we have to divide by a half to kind of counteract that 2. So 1 half times 2 is 1, so nothing really changes. So these two integrals are still the same thing. And now notice that we have an extra x right here, and in order to get the extra x, we're going to have the integral of 2 natural log, or 2x natural log of x, and we want this extra x, so let's put it in. But we can't just put it in x because that's going to change the value of the integral, so we'll subtract off an x right away in order to preserve the value. And this is now equal to 1 half. And now let's use the linearity of the integral to split this integral up into 2 parts. So we have the integral of 2x natural log of x plus x dx, and now we have minus the integral of x times dx. And this as well, notice that 2x natural log of x plus x is exactly this expression, which is the derivative of x squared natural log of x. So we have 1 half times the integral of the derivative of x squared natural log of x dx, and then minus integral of x. That's pretty easy to evaluate, just some power rule. So 1 half x squared, like so. And if you have an integral of the derivative, well, that's just the function itself. So you end up with 1 half times x squared natural log of x, and we can distribute this 1 half into here as well. So that's 1/4 x squared, which is more or less what we have over here. So we've shown that. For part C of this question, we have some more integration, so we have to find the area bounded by the line x equals a, the function f itself, and the x-axis. So what is the line x equals a? Well, we know what this minimum coordinate is. It's 1 over e comma minus 1 over e. So that means a is equal to 1 over e. So let's do that replacement. So let's shade in the area we have to find. It's always nice to shade in the area so you know what you're trying to figure out. So we have the line x equals 1 over e right there. And we have to find the area bounded by that line, the function f of x, and the x-axis. So we're trying to find this region in here. And in order to do that, that's quite easy. We just take the integral from 1 over e to whatever this intercept is over here. Let's just put question mark for there for now, of the function f of x dx. But notice one crucial thing. This f of x is actually negative on that interval. So we have to multiply the integral by a negative in order to kind of flip the area up to the top and make it positive. So what is this question mark? Well, it's just the x-intercept of f of x, and you can find that quite easily by solving where x natural log of x is equal to 0. Well, you obviously have the solution x equals 0, so let's divide both sides by x, and we have to solve where natural log of x is equal to 0. Well, natural log of 1 is equal to 0, that means x is equal to 1, so this coordinate is in fact a 1 comma 0. So now we integrate from 1 over e all the way up to 1 of f of x, but we know that's the integral of 1 over e to 1 f of x is x natural log of x dx. But we showed from the previous part that if you differentiate x times the natural log of x, you get something like 1/2 x squared natural log of x, and we have to evaluate this at its bounds. So from 1 over e to 1, you'll also have a negative, and I'm also going to do one slight trick. We can distribute this negative into these bounds by switching them around. So it would be the same thing for the integral. We can distribute the negative into the integral by switching the bounds around. So now we have the integral from 1 to 1 over e, and now it's simply a matter of just subbing in these bounds. So let's figure out the bounds at 1 over e. So plugging in 1 over e into here, we get 1/2 1 over e squared. Natural log of 1 over e, we know from before that it's equal to -1, so -1 like so. And then we have a minus. If you plug 1 over e into here, you get 1/4 1 over e, but the whole thing's squared. So that's the first part of integration. Now for the second part of integration, we subtract off. Now notice if you plug 1 into this natural log, it's equal to 0 because natural log of 1 is 0. So this whole entire part kind of disappears and you're left with a minus. Now plugging 1 into here, you're just left with 1/4 like so. Alright, very fine. And now let's see what we can do. Over here, in this first bracket, we're left with a -1 over 2e squared. So we have e squared multiplied by 2 like so. Then we also have a minus. Now this is going to be 1 over 4 times e squared. So we have e squared, multiply that by 4. Okay, now we have double negative, so this becomes a positive 1/4. Okay, let's try to combine these two fractions together. Notice that we can multiply the top and bottom by 2, which gives us 2 over 4. And we're left with -2 minus 1, which is a -3. So this is -3 over 4e squared plus 1/4. And you can switch these around to make it look a bit nicer. So the final answer is 1/4 minus 3 over 4e squared. And that should be your area. For the next question, part di, we're given this function, this new function g, which is defined from a to infinity. So I guess g would start from this point A and travel all the way up to infinity. So it's f of x plus k. So we have this original f of x, and we can translate it up and down however we want. And we have to find the value of k such that the line y equals 2x is tangent to g. So first of all, what I did was I took a look at the function g of x, And if it's tangent to the line y equals 2x, that means somewhere on g of x, the gradient must be equal to 2. So what I did was I took g prime of x, I took a look at that, and that's exactly f prime of x. You can use some of your working out from part A, so derivative of f of x is exactly natural log of x plus 1, and we have to solve, so this is the gradient of g, we have to solve where the gradient is equal to 2. So that gives you natural log of x is equal to 1, and where is natural log of x equals to 1? Well, x is equal to e. Because if you plug e into this natural log, you get 1. So if you have the graph y equals 2x like so y equals 2x, and x is equal to e, which is right here, so x equals e, that means the corresponding y value is y equals 2e, because if you plug e into here, you get 2e. And if the graph g is tangent to this line, y equals 2x, that means at the point x equals e, its y coordinate must also be 2e. So we have to sub this x value back into g, so g of e must give you 2e. But what exactly is g of e? Well, g of e is exactly f of e plus k, but f of e is e natural log of e plus k. Natural log of e, we know that's 1. So we end up with 2e being equal to e plus k. So that implies that k is equal to e. And that's the solution to this first part, di. Now for the second part, di, this is where things get a little bit more spicy, d and double I. We have to find the values of k such that the functions g and the function g inverse don't intersect at all. So in order to solve this, you have to have a little bit of graphical intuition. I guess I'll rub out this. So if you look at the graph, g of x looks something like this. So it's just f of x translated up or down by something. And if you have a look at the corresponding graph of g inverse, well, first of all, g actually starts from this stationary point over here, so it shouldn't start from 0. It should start from whatever that stationary point is. G inverse kind of mirrors this original function. And notice one thing in particular, g and g inverse, so this is g inverse and this is g, both of these graphs are symmetric across the line y equals x, like so. So in fact, the only way for these two graphs to not intersect is if g is always above y equals x, because if g is below y equals x, then what happens is that, well, you get a graph of g that maybe looks something like this, and that means your g inverse will take on a shape maybe something like this, and as you can see, they will intersect, which isn't good. So if g is always above y equals x, g and g inverse will never intersect. So the goal is now, we can reframe this question as asking, finds the value of k, so finds k such that for all x, I guess on this interval, so 1 over e comma infinity, we have the function g of x, so g is always greater than x. So we have to find this specific value of k. And in order to find this, let's take kind of like the borderline case where g only intersects on this tangent line once. So we can kind of use the method we looked at in the previous question where we make y equals to x tangent to the function g. So that means g prime must be equal to 1, but g prime is natural log of x plus 1. And if we're solving where that equals 1, that means natural log of x is equal to 0, which implies that x equals 1. And if x equals 1, that means the corresponding y value is equal to 1. So that means g of 1 is equal to 1. But g of 1 is f of 1 plus k, and that's equal to 1. But f of 1 is just, well, f is equal to natural log of x times x. If you plug a 1 into here, you're going to get 0. So 0 plus k gives you 1. That means k is equal to 1. So if k is equal to 1, you only translate the graph f up by 1 unit, and you end up with a graph g that intersects this line y equals x once it's tangential to that line. So if you choose any k value that's greater than 1, you're going to keep pushing this graph g up and up even more, and you're going to keep pushing this graph g inverse to the side more and more, and they definitely won't intersect. So if you choose k equals to 1, then g and g inverse will intersect at that one point on the line y equals x. But if k is any number greater than 1, then those two graphs will never intersect. So the final answer is that k is greater than 1. And that is pretty much it. That is my solution to this year's exam. That's how I approach most of the questions on this exam, except for the one where I got wrong. I actually used some other weird method and ended up with the wrong answer. But I'm pretty sure that would have been inconsequential because the method was correct and everything. I guess interpreted a couple of things wrong. So yeah, I hope you guys enjoyed this video. Hope it helped if you guys needed help with answering questions from this exam. But yeah, have a wonderful day as always, and I'll see everyone in the next video. Bye bye.